The sky may not be blue, but in my heart, it is so blue out there.
It was snowing at 12 o'clock
I don't know about you guys. I'm pretty excited to have about 10 days off.
Oh my god.
That's going to be nice.
Oh yeah.
So let's see. All we got to do is get through this this hour. I guess I'm going to get through 2 hours, but that'll be manageable. So funny enough, I uploaded the last I guess Wednesday's podcast to YouTube, and he tagged me and was like, "Your video has been blocked globally for copyright infringement." And I was like, "No one's copywritten my lecture. That's not true. Or copyrighted my lecture, I should say." And so apparently, it picks up like the text songs that are on, that are in your video. And so it was like, yeah, like Apple Corp, the Beatles company, have blocked your video or your globally. And I was like, oh, okay. So I got to be careful to make sure I turn the music off before I start recording, I guess.
Oh my god.
All right, so today's going to be pretty light and easy. And then Monday after spring break, we're gonna get back and hit it pretty hard. So we're gonna go really organic-y after spring break. From here on out, it's pretty intense. So just a heads up. But today we'll save that for after spring break. Also, I had it pointed out to me that I've scheduled an exam the Monday after Easter. And so for those of you that I guess celebrate Easter, we might end up pushing that exam to Wednesday. If you still want to take it.
Yeah, no. I'll take the Monday. Take the Monday.
All right, so this is a bio exam on Wednesday. If that becomes an issue, if you need to celebrate Easter and won't have time to study on that Sunday, I may just let me know and I can maybe let you take it Tuesday. I can only push it so far back, so we'll talk. I'll think about it over spring break. We'll talk about it, see if we can get something figured out. Okay, so last time we left off, we just discussed some rotation of polarized light by chiral compounds, and so we can go on and talk about that a little bit more. So what we can do is we can define as percent, so we'll write in blue for blue sky today. So we'll talk about the percent optical purity. And so this is you're going to look at this sort of thing in lab. And so what it is you take a look at the rotation of a sample. So we say the alpha of some given sample. The optical purity is basically, it's going to be this ratio. And so the bottom part of our fraction is going to be the rotation of a pure enantiomer. So we just pick one of the pure enantiomers. And so you can judge how basically pure you've got your sample. Since these things have the same physical properties, it's pretty much the only way that we can tell. And so since that's a fraction, we will multiply that by 100%. And so for example, if we had some given sample with a rotation of 30 degrees, and we know that the pure, we'll say R form, it doesn't really matter, we'll say the pure R form, or the R enantiomer, has a rotation equal to 75 degrees. Well, if we wanted to talk about how pure our sample is in terms of enantiomer purity, we would say that, well, we've got plus 30 degrees divided by plus 75 degrees times 100%. And so that would equal 40% purity. Okay, and so another thing we can do to define enantiomer purity when we're talking about compounds is you'll see it talked about as enantiomeric excess. And so this is pretty common in real-world terminology. If you publish a paper and you're publishing a paper of a reaction that is enantioselective, meaning that it's giving one of the enantiomers, you will see basically you'll describe your purity using enantiomeric excess, and so you'll see that sometimes shortened to EE. And so what that ultimately is basically you're going to take one of your percentage of it, and you're going to subtract from that the other one. Or you could go the other way. You could also say the percent S minus the percent R. And so importantly, these two things, this percent optical purity along with this enantiomeric excess, they're equal to each other, right? And so we definitely want to put down percent optical purity is equal to EE. So we can go from one to the other pretty much directly. All right, so talking about our example above, if we had a pure, or at least of our sample, we found had an optical purity of 40%. And so we were comparing that to the R enantiomer. What we can say is that our sample is going to exist as 40% R. So we've got 40% that is pure R. So the other 60%, what is that? Well, it's not S, right? Because think about it. Think about what we've got. If we say that the pure R enantiomer rotates at plus 75 and our sample rotates at plus 30, well, what do we clearly have more of, R or S? We clearly have more of R, and so what that means is that 40% of it is R. We've got 60% that is racemic. And so ultimately that's going to be another 30% of R along with 30% of S. And so that explains why we ultimately see positive rotation like we would see for our pure R enantiomer. It wouldn't make sense if we had 60% S, then it would rotate like the other way. So ultimately in our sample, what we've got is 70% R and 30% S. And so that's basically where we derive that from looking at the optical purity and then thinking about it in terms of EE. And then ultimately we could find the total composition of our mixture. Okay, so that's optical purity. And then so finally, we're just going to tie up some loose streaks here. So we've talked about chirality. And so finally, this last section, we'll talk about the separation of enantiomers. So you'll also see this described as the resolution of enantiomer. Okay, so I've said all along, enantiomers, when we talk about chemical or physical properties, are they the same or are they different? They're the same, and so if we want to separate those two special, if we want to separate one enantiomer from the other, how easy is that going to be? They have the same melting point, they have the same boiling point, they have the same polarity, so we can't do it via distillation, we can't do it via chromatography, and so it is. It's very, very difficult, but there's a trick that we can use. So enantiomers have the same physical properties, but what about diastereomers? They do not have the same physical properties. So what we want to say is that, first off, separation of enantiomers is not possible since enantiomers have the same physical properties. But diastereomers have different physical properties. Now, in reality, there are chemical or physical methods to separate enantiomers. So in the real world, what we have is chiral. So you know how we have a column in the GC, right? And it separates things based on polarity. Well, there are also chromatography columns that are basically chiral environments. So people make these columns packed with sugars, and sugars are definitely chiral with all these stereos in it. They're not very efficient, and so you can't actually do this in any large batch, but on a very small scale, it is possible. There is technology that has been developed to do that. But let's say we had 10 grams, and we wanted to separate that from another 10 grams of the end. It's going to be really, really difficult. So not going to be possible. And so, for example, the way that this is basically fixed is let's imagine that we have a racemic mixture of acids. All right, so we have a racemic mix of acid, and so we're going to have the R form as well as the S form, and they're going to be there in equal amounts. Okay, so what we've got is we've got our R acid and we've got our S acid. Now, the relationship between the R acid and the S acid, what is that relationship? It's enantiomers, right? It's just the other handiness. So we've got enantiomers And so those are inseparable because they are enantiomers. But what we can do is if we're able to obtain a chirally pure form of something, and for example, glucose. We have chirally pure glucose. We only have one handedness of that. Our body only utilizes one of the enantiomers of glucose. And there's plenty of molecules, for example, amino acids, that you can just buy in the pure enantiomeric form. And so what we could do is we could react this with basically an enantiomerically pure form of a base. So we're going to have a chiral base, and in this case it's just the R form. All right, so we undergo this reaction, and so what's going to come out is we're going to have an RS, acid-base salt, remembering salt is the product of an acid-base reaction. And then likewise, we're going to, hold on, actually the top one would be RR, and then the bottom one would be our RS, acid-base salt. All right, so now when we talk about the difference between these two molecules, are they still enantiomers? They're not, right? Because we don't have both chiral centers flipping. And so what are they if they're not enantiomers? Yeah, now what we've got are diastereomers. And so those definitely are separable because they do have different physical properties. And so what we'll do is we'll take our racemic mixture here, we'll basically react it with something that's enantiomerically pure to make these diastereomers. At that point we can separate them, and then we'll just get rid of the base, and what we end up with is a pure sample of R acid and then another pure sample of S acid. So that's typically how that's done. That's it for chapter 3. Ooh. Yay. Chapter 5 is a silly chapter, by the way. I don't know. I don't have any idea why chapter 5 exists differently from chapter 6. I don't know. Yeah.
What exactly does racemic mean?
It is a 50-50 mix of enantiomers. Yeah. So anytime you see a racemic mixture, you're talking about a 50-50 mix of enantiomers. All right. So basically, my goal is to get through all of chapter 5 today because it's a silly chapter, like I said, and we've actually already covered a lot of what's in chapter 5 when we talked about cis, trans, double bonds, and easy. I saw no reason to not keep that with stereochemistry, so that's what I've done. So we've already covered some of it. This is basically going to be an intro to alkenes. So alkenes are, they're very similar to alkanes in that they're mainly just carbons and hydrogens, but the fact that they have some unsaturation is going to make them a lot more reactive than alkanes. So here's how this next few weeks is going to go down. So we're going to talk about chapter 5 today. And then after spring break, we're basically going to spend about 2 weeks talking about the reactions of alkenes. And so we're going to learn 12 or 14 different reactions that alkenes can do, their mechanisms, their stereochemical results. And so for those of you that came to class, I'm going to give you a big leg up on how you're going to master this material. So you hear 12 to 14 reactions, and what a lot of people are going to do is they're going to try to memorize each reaction, but ultimately what we've got are 3 classes of reactions, and so all of those 12 or 14 reactions we're going to learn are going to fit into one of these 3 classes that are mechanistically the same. And so as long as you have those 3 different types of mechanisms basically understood, you're going to be perfectly fine. What you don't want to do is spend all your time basically trying to memorize everything about these 12 or 14 different reactions, because if they fit into one class, we're going to see that they basically have the same, what we'll learn is regioselectivity, stereoselectivity, and ultimately reactivity in general. So definitely, that's a little preview, I guess, for after spring break. Look, we're just going to focus on the big picture. Don't try to learn all of the little details as we go. All right, so chapter 5, alkenes. This entire chapter is pretty much just an intro into alkenes. Again, I don't know why they made it, so I thought it would be interesting to think about fatty acids and kind of connect this to the real world. So when we talk about fatty acids, we have types of fatty acids, and so you've certainly heard of saturated fat, and you've heard about unsaturated fat. Okay, so an example of a saturated fat would be palmitic acid, and so that thing's got 16 carbons, and that's pretty typical for fatty acids. You're going to have very long carbon chains and then a polar end. And so for palmitic acid, it's going to be 1, 2, and then we've got a carboxylic acid at the very end. So this is C16, and so it is known as palmitic acid. That's a common name. All right, so palmitic acid is an example of a saturated fatty acid. And so when we talk about the source of saturated fats, if we think about animals or plants or fish, what's typically higher in saturated fat? Animals are most certainly higher in saturated fats. All right, and so the melting point of a typical saturated fat, such as palmitic acid, is going to be right around 63 degrees Celsius. Now, is that a solid or a liquid? At room temperature. It's a solid at room temperature. All right, so whenever we think of animal fat, typically that's going to be a solid fat, and that's because they are saturated and they have these boiling or these melting points at 63. So then an unsaturated fat is essentially going to be a fat that has a kink in it, and the kink is due to a double bond. All right, so we've talked about how hydrocarbons are saturated, and certainly when we look at the saturated fat, you can see at least the carbon chain is saturated. But now in the unsaturated fat, we have at least one double bond, and so you'll see unsaturated fats that can have 2 or 3 or 4 basically double bonds in them to make them unsaturated. And so typically you're going to find that these are going to be cis double bonds whenever we have them in natural sources of unsaturated fats. And so the typical places that we find unsaturated fats are going to be plants and fish. And so one thing about an unsaturated fat versus saturated fat, so you can see that the melting point is going to be 13 degrees Celsius. And so at room temperature, an unsaturated fat is going to be a liquid or a solid. It's going to be a liquid. And so that has the disadvantage of if it's a liquid, it reacts a lot more quickly. And so when we think about oils and fats going rancid, liquid fats will typically go rancid a lot more quickly than solid fats. All right, so there's a downside to all this. So who's heard good things about hydrogenated fats or oils? Typically, when you hear about hydrogenated fats and oils, is it good or bad? It's typically a bad thing for health reasons, and so let's talk about why that is. So, the product, what it is basically what chemical suppliers or food suppliers can do is they can take these unsaturated fats and they can hydrogenate them. Basically, they can add saturation so that they become more saturated. And so, what happens is the product resulting from hydrogenation, or the hydrogenated fats will be the product resulting from the hydrogenation of unsaturated fats. Why do you think companies want to do that? It doesn't go bad as fast, right? We said that liquid fats are typically going to be, they're lower melting, and so they can go rancid faster. So the pros to hydrogenated fats, we would say longer shelf life. So things like margarine. Margarine is a thing because it has a longer shelf life. That's why been so popular for so long now. All right. Furthermore, it is solid. And so it's easier to transport and package solids than it is liquids, right? Liquids can leak. All right, so the downside to using hydrogenated fats is that ultimately they are bad for cholesterol and heart health. Kind of a double whammy here. But it's not maybe why you think, although it is linked to something that I know most of you have probably heard of and probably have not put together when it comes to hydrogenated fats. And so what happens is when companies take these unsaturated fats, and so for example, there can be lots of different cis double bonds, they're not able to hydrogenate all of them. But what does happen is the isomerization of some of these cis double bonds. And so if we have a cis double bond that isomerizes to the other possibility, well, if it's not cis, what does it become? Trans. And so who's heard of trans fats? That's why trans fats are best. So trans fats ultimately lead to high cholesterol and heart health. And so that's kind of the downside of making things like margarine is they try to hydrogenate everything into this form, but they're not able to. And so some of of the cis double bonds become trans double bonds, and trans double bonds are known for being pretty bad for your health. And so that's where the idea of trans fats come from. So ultimately, these unsaturated cis fats are changed to trans fats, and so those are bad for cholesterol and heart health. Okay, so double bonds have a pretty important role medically. We're basically just going to hit some bits and pieces as we go. I'm just going to try to summarize Chapter 5 into one day. We've seen a lot of this material. So when we talk about the geometry of a double bond, we can draw it one of two ways. So we can draw it with our trigonal plane and the plane of the board. And so if we draw our carbons, our sp2 hybridized carbons in the plane of the board, where will our p orbitals be? They have depth, right? So they'll be perpendicular, they'll be in and out of the board, and so how do we draw that? On a diagonal, right? That's how we indicate depth on the z-axis. Or, I think the picture that better shows, and this is what I put on the exam to see who really understood where these orbitals go, if we change our trigonal plane such that now the plane itself has depth, where will our p orbitals go?
Up and down.
Yeah, now they go straight up and down. So they're always going to be perpendicular to our sp2 trigonally planar carbons. All right, I've said this a million times. We'll say it again. No bond rotation and a double bond. And so again, the reason for that is if we have a bond rotation, we basically have to break our pi bond. We no longer have a double bond. And generally, we don't have enough energy in the molecule to do that. Certainly you can heat it up to a bazillion degrees and it might be able to undergo that bond rotation, but at room temperature, it's just not going to happen. All right, so we've got two different forms. We've got a cis double bond. So for example, a cis double bond we draw with some sort of non-hydrogen substituent on opposite sides. And so when we're naming, we can think about how we would name this molecule. So first off, we've got a long carbon chain of how long? All right, so we've got 4 carbons, right? We can count 1, 2, 3, 4. And so if we count 1, 2, 3, 4, we're going to use what root? Bute. And then how do we end it? It's no longer butane. If it has a double bond, it is. Yeah, it is now butene. And so what we'll do is we'll indicate where that is. Now, it doesn't matter how we're going to count because it's symmetrical, so we could say 1, 2, 3, 4. And so if we had to give a location to our double bond, what number would we use? We would use 2, right? So it's assumed that the double bond is going to go down the chain, and so we know by saying 2 that it's going to be between carbons 2 and 3. If instead it were between carbons 1 and 2, what would we call this?
1.
We'd call it 1-butene. All right. So furthermore, we have possibilities between cis and trans, and so if you want to specify the stereochemistry, which you should certainly do, we said that is trans 2-butene. We've also got the other alternative, where we're going to have the same connectivity, and so in this case, it's going to be the same naming scheme, except instead of trans, it's going to be cis 2-butene. All right. So let's think about between cis and trans, what do you think is more stable? Why trans?
Because there's no less interaction.
So let's think about groups in space. So what's more likely to have any steric clash, when we've got methyl groups on opposite sides or when we've got methyl groups on the same side? The same side. And so if there's going to be more steric strain when our groups are on the same side, what's going to be the more stable form? Yeah, it's going to be trans. And so what we can say is that in general, trans is more stable due to steric strain than cis. All right, so that steric strain is basically now we've got our methyl groups on the same side, and so we can have a little bit of interaction, and any interaction that we have is going to be strain energy that ultimately raises that form in energy. So cis is higher in energy. Okay, so let's do some nomenclature things. All right, so we already know this. number one, we always want to make sure we change our ane to ene, right? So butane becomes butene, propane becomes propene. All right, so we do that. Furthermore, we've already discussed this, but the DB, what do you think DB stands for? Double bond. So the double bond is located using the number of its first carbon. And we've been doing that. That's why we called this 2-butene, not 2,3-butene. All right, so let's see. If we go to number 3, what we find is that numbering, and this is a new twist to things we've done before. We say that numbering must absolutely give the double bond. Let's see. Make sure I state this the right way. Yeah. So numbering must give double bond the lowest number. And so that means we could have a molecule with lots and lots of different substituents. We could encounter a substituent on carbon number 2 or even on carbon number 1, but it doesn't matter. We always want to make sure that we're giving the double bond the lowest number. So basically the double bond takes priority over any substituents. And so an example of that, we could use this molecule. So let's see. All right, so we've got 2 possible ways to draw or to number. We could say 1, 2, 3, 4, 5, or we could say 1, 2, 3, 4, 5. And so the rules that we've learned up until now, we'd say, well, bromine's on carbon number 1. Certainly we would number left to right, but of course that would give the double bond a 3, whereas if we counted right to left, it would give a double bond to 2. And so we're going to use red or green. Yeah, we're going to use green. So that's the correct way to number. And so our longest carbon chain is 5, and so that's going to be pentene. We locate our double bond at number 2. Now we also need to say something about that bromine, so what would we call that?
Bromo.
Bromo, and so what position is it at?
5.
Yeah, it's at 5, so we end up with 5 bromo, 2 pentene. You don't want to say 1 bromo, 3 pentene, because now we have not given the double bond the lowest possible number. All right, so that's a change in rules. Another one, and honestly, so that was pretty easy to remember, and this next one's pretty easy to remember. So the parent chain must contain a double bond, or the double bond. And so for example, we could have a molecule that looks like this. And so what's our longest carbon chain in this molecule?
9.
It's 9, but does that include our double bond?
No.
It doesn't. And so what we've got to do is we've always got to count the longest chain, including the double bond. And so in that case, how long is it?
8.
It's 8. And so we would call this thing, what root?
Octene.
Yep, we'd say octene. And so how we would number is we'd number giving double bond the lowest possible. So we end up with a name of 3-propyl 1-octene, like that. Does a terminal double bond ever have stereochemistry?
No.
No, there's no way to prioritize, so we don't have to include a cis or a trans or anything there. And in fact, if we go back up, and what we should really say is we should add to this 5-bromo-2-pentene to the beginning what word? To indicate stereochemistry. Cis or trans?
Trans.
Definitely trans. Or you could use E or Z, so what would you use there? Yeah, or you could say E. So typically when we write stereochemistry in using EZ or RS, we put that in a parentheses like that. Yeah?
Explain again why the terminal ones don't have.
It's because we have to prioritize, right? We have to figure out if it's cis, trans, or EZ, and so ultimately, off of one of these carbons, we just have 2 hydrogens, and there's no way we could pick one of those to be higher priority, and so we can't really pick one of those names. Yeah. No stereochemistry in terminal double bonds. All right, so then we'll do 2 more rules. So rule number 5 is going to be that the double bond always gets numbers 1 and 2 in a cycloalkene So furthermore, we always, and this harkens back to rules that we've learned before, we always number in the direction of hitting first substituent. All right, so we'll do a couple of examples of that. So substituent.
But that only applies after you've gotten the double bond.
Yeah, we always have to give the double bond 1 and 2. But we could, if we've got a cycloalkane, or a cycloalkene, we could either number it clockwise or number it counterclockwise, and so the way that we decide is just whichever hits a substituent first, not counting the double bond itself. Okay, so for example, we could have this molecule right here, and so we have to number either 1, 2, or 1, 2. Okay, so looking at that double bond, we have a couple of, or at least on this molecule as a whole, we've got a couple of methyl groups, right? And so if we use the red numbering, we hit one of the methyl groups on carbon number 1. If we use the green numbering, we hit the methyl group on carbon number 2. And so which would we use, red or green?
Red.
We definitely use red, and so we'll go ahead and number all the way around. And so we end up calling this 1,3 dimethyl cyclohexane. Do we have to say 1 cyclohexane? No, because it's understood by rule that we're always giving the double bond number 1 and number 2. If you said 1 cyclohexene, that's fine. I know what you mean. But it's not necessary. If you leave it off, you still get full credit for that. All right, another example. And this one looks a little more unintuitive. So if we had this molecule. Okay, so again, we could number 1, 2. And that would give the second chlorine a number 6, or we could number 1, 2 like this, and that would give the second chlorine number 3. And so we talked about using the lowest sum when we were talking about cycloalkanes, but following our rules for cycloalkenes, are we going to use the red or the green?
Red.
We want to use the red because, again, it's just the first substituent that we hit. And so we have a substituent on carbon number 1 if we use the red versus carbon number 2 if we have the green. Yeah?
So if somehow the double bond ends up being 2 substituents, we can use the other rule where the heavier substituent would be the
Yeah, and so if you had something like this, obviously you can't use either of the substituents on the double bond, and so you would then use the green because our first substituent would be on number 3 in that case. Yeah. But I'm not really teaching that rule, so. Okay, so we would name this 1,6-dichloro cyclohexene. And again, we don't have to say 1 cyclohexene because it's assumed that the double bond is on carbons 1 and 2, yeah.
You wouldn't even use the numbers, the green numbers, because like the sum is less than 7, like 5 is less than 7.
Yeah, and so in this case, when we have cycloalkenes, when we have a double bond in the ring, we no longer consider the lowest sum rule. Yeah, so that goes out the window because the numbering ends up being different because we have to make sure we get the double bond 1 and 2, yeah.
What would you do in the case of multiple double bonds?
So we'll look at a couple of examples of that in a minute. We're not going to have too many complex cases of that, but we'll at least learn how to name it. Yeah. Okay. So there are also some common names involved in double bonds, and so one of these is if you have a molecule, our simplest alkene, using IUPAC naming, what would we call that? It's a carbon chain of 2, and so we'd call it not ethane, but ethene. No one calls it ethene. You'll never see this referred to as ethene. What that is called is ethylene. I don't know. It's how it is. No one. It's sort of like also if you see this molecule, which you might call ethine, no one calls it that. That is acetylene. Common names. I don't know. I don't have an explanation for you. So you'll never see ethene called ethene. You'll always see it called ethylene. If you were to call it ethene, I'm perfectly fine with you using the correct IUPAC nomenclature, right? So that's fine. But in your general day-to-day life, you'll never see that called ethane. All right, we have substituents with double bonds that are given common names, just like we saw things like tert-butyl or isopropyl, and so we'll just look at two of those. So one of them is going to be this substituent, and this is referred to as an allyl group. Again, it is. And then the other one we'll talk about. And I just write these two because these two are the most common that you're most likely to ever see as you go about your careers. This one will be referred to as a vinyl group. All right, so especially you'll see like PVC pipe, right? So that's it's a polymer, and so those things are named after. So what's a polymer? It's a really long molecule, right? Got like hundreds or even thousands and thousands of basically units connected together. So they're huge molecules. That's what gives polymers their special properties. And so we name polymers based on the monomers, or the individual units that make up each link of the chain. And so PVC is called polyvinyl chloride, and so that's where the vinyl comes from, right? So it's going to be because it contains this group right here. Yeah.
Is there vinyl and vinyls?
What is it?
Is there vinyl and vinyls?
Maybe. I don't know. I'm not sure I don't know what chemically the composition is. Yeah, I don't know. But you'd think maybe,
Yeah,
right?
I mean, it makes sense.
It makes sense.
Logically,
Yeah.
you're calling it vinyl.
Okay, I'll look that up. What's it? Okay. Let's see. Oh man, we're totally gonna get through chapter 5. This is awesome. Okay, so let's just do a few more naming examples, and then look at a couple really short things, and we'll just call it spring break. So, what we can have, yeah, we did one chapter in less than a lecture. That's pretty good. All right, so we have a molecule that looks like this, and we want to name it. All right, so what's the longest carbon chain?
3.
Yeah, so we've got 3 carbons. And so we want to number it how? We want to give the lowest number to the double bond, right? And so we'd say 1, 2, 3 is definitely how we're going to name this or number this thing. And so we'd say our 3 carbon chain is going to be a 1 propene. Let's think about this. Would we ever have a 2 propene?
No.
So we'd have this, or we'd have this, and those are both going to be a 1 propene, right? Because we start. So you don't even have to include 1 propene in this case, because you're never going to have a 2 propene, because the numbering would be wrong. All right, so then we've got, let's see, we've got a double bond, and so can we use cis or trans here? No, we can't, because we have 3 groups, right? So anytime we have more than 2 groups, we have to use what kind of nomenclature? EZ, and so we need to prioritize. So on the left side, bromine is going to be our higher priority. On the right side, which is it going to be? Iodine, because of atomic weight. And so that would be E or Z? Z. Yeah, that would be Z. And so let's see, what else do we need to do? So we just need to name our substituents at this point, and so we should see how we can do that. So we're going to say that this is Z. 1 bromo, 2 iodo. And so why does bromo come before iodo?
Because B comes before that.
Why? How do we decide which substituents come first? Alphabetical. That's it. It's just alphabetical. So we say 1 bromo, 2 iodo, and then we could say 1 propene, or we could just say propene because it's not ambiguous to say just propene.
So if the iodine were over there, it'd still be 2 bromo, 1 iodo?
Yeah, so if our molecule instead was this, we would call that C2 bromo,
Okay.
1 iodo propene. So it's just alphabetical, is why bromo is always going to come before iodo. Yep.
Why is there a 2 on both the CH3 and the H?
So that was just the green is just the priorities and figuring out the double bonds.
So those are the same priority?
So what we do is we look So basically, we look at the two substituents on one carbon of the double bond, then we look at the two substituents on the other one. And so bromine is higher priority than hydrogen, and then iodine is higher priority than methyl. Yep.
So is the one in one protein necessary?
No, you could just say propane. That'd be perfectly fine. Because we'll never have two propane. All right, let's get a little more complicated. All right, so let's draw a molecule. So it looks like that. All right. First off, how many stereoisomers are going to be possible for this connectivity? So we count up how many sites of RS and EC. And so how many are there? There's 3, and so it's 2 to the third. So there's how many possible? 8. So there's going to be 8 possible stereoisomers here. Right? All right, so let's see. First off, what's the longest carbon chain? It's the only carbon chain, right? 6. I count 7. So 7 carbons. And so in this case, we have to make sure we include a 2 heptene, because we certainly could have 3 heptene or 1 heptene or 4 heptene. No, wait, would we ever have 4 heptene? No, we'd never have 4 heptene, because ultimately that would just be 3 heptene, right? So, okay. So then we've got a chloro and a bromo, and so of course if we're actually going to name this thing, every stereoisomer gets its own name. So what do we have to do with these chiral centers? We got to label them, right? If we're going to name them, we have to label them. And so that means, of course, we've got a hydrogen going back, and here we've got a hydrogen in front. So we have to prioritize. We'll prioritize 1, 2, 3, 4, like that, right? So bromine's first, hydrogen's fourth, and then here we've got a CH2 with a carbon, here we've got CH3, so that one's going to be this one. And so in numbering, all right, we can go hydrogen in the back, and we number with our left hand, 1, 2, 3. Nope, and so we go the other way, in the back, 1, 2, 3, and so we do see it's going clockwise, and so that's RS, or it is R. And so the other one, we've got 1, 4. Which one's going to be 2? This one or this one?
The bromine. Bromine,
So let's think about what the connectivity is. So going to the right, we say, all right, there's a double bond there, and of course there is a hydrogen off of this. So what we draw is basically this. We consider that double bond twice, right? We say that it's connected to 2 carbons because it is connected to 1 carbon twice. And so then going the other way, what we've got is basically carbon, hydrogen, hydrogen. So what's higher priority? Definitely the one on the right, right? So we call that 2. In this case, it's going to be 3. Okay, so then we have to use our hand trick, and so if we use our right hand coming out this way, we count 1, 3, 2. So then our left hand is 1, 2, 3, and so if it's our left hand, it is S. Okay, so let's see. We still have to. Let's go ahead and number our chain. A lot of numbers on this molecule. All right, so we're numbering 1, 2, 3, 4, 5, 6, 7. So we know that we're going to have ultimately an S. For bromo, we're going to have, for chloro. And we have, what's up?
No.
Yeah, I screwed that up. All right, so then R6 bromo. I kind of like this smaller class size. It's a little more informal, feels like. All right, so S4 chloro, R6 bromo. And so the double bond, is that E or Z? They're on opposite sides, and so that is going to be E, or we could say trans in this case, but I like to stick EZ because it's easier to remember. Okay, so then how do we do this is basically the new stuff for this problem right here. So this is all information that we should have been able to figure up until now, and then when we name this, what we're going to say is we write a name that is, all right, so at the beginning we put a parentheses, and so inside this parentheses at the beginning is where we're going to put all of our stereochemical information. And so what we'll do is we'll say that we've got 2E, 4S, 6R, and then we just name it normally, right? So we figured out basically what the stereochemistry is at each carbon, and so let's see, we call this 6-bromo, 4-chloro, 2-heptene, like that. Okay, so that's the new part. That's basically where we're going to put all of our stereochemical information. We just put it in parentheses at the beginning, and the way that we can tell which R goes to which carbon is we just put the number next to the R, and so that tells us where our stereochemistry is. All right, really quickly, we can have cycloalkenes. And so the only point I'm going to make about cycloalkenes is we're going to say that cyclooctene is the smallest trans cycloalkene. All right, so for example, if you tried to draw, say, cyclopentene as a trans double bond, what you'd end up looking at, all right, so that's already 4 carbons, right? So the other one would be, I guess, behind there. All right, so that's ridiculously unstable, right? Those bond angles are not going to be good. And so basically, anything smaller than an 8-membered ring, if it has a double bond, it's going to be cis or trans. It's got to be cis, otherwise the geometry is really, really wonky. So what you'll see for cyclooctene is it can have both a cis double bond, and I hate drawing this, the trans version looks something like that.
Looks like
1, 2, 3, 4, 5, 6, 7, 8. Yeah, it's not good, right? So there's still a lot of strain energy, but there's not so much strain energy that this thing's just going to blow up. So it can exist as the trans form. So this is trans, and this is cis. And so finally, our last bit, we can talk about polyenes. And so if we have 2 double bonds, we're going to refer to something as a diene. If we have 3 double bonds, we're going to refer to it as a triene, et cetera, right? So tetraene, however we would go. So if we see a compound that looks like this, all right, so our longest carbon chains, we number to give the double bond the lowest number. If we number the other way, then the double bond on the right would be given 1, 2, 3. So we know we want to number left to right. And so here we've got a Z double bond. I guess here we've also got a Z double bond. And so in naming this, we would call it 2Z, 7Z, 7Z, 2, 7. What's our root name for 10?
Dec.
Dec. And so we call it decadiene instead of decene. So that's chapter 5. We're done. Have a good spring break.
You too.
Yeah. I plan on getting lots of problems out for stereochemistry over spring break as early as possible. So be on the lookout for those.
Sometimes I just see you drop down. Are you power stancing?
Yeah, dude. I get down.
Oh man, you getting into this?
Yeah, I gotta bounce around.
I like it. Well, have a great spring break.
Yeah, you too, Caleb. What's up? Are you paying for parking in Richmond? All week?
No, I'm just parking the car here.
Okay, I just didn't know if you were, because I was gonna say I'll give you a lift instead of.
Oh no, I mean you don't have to. No.
Okay. Yeah. So my goal was to probably leave here by 4ish.
Yeah.
Does that work?
4. Yeah, that works.
I'll let you know if it'll be. It could be earlier. I'll let you know if it will be. I'll try not to forget about you this time.
Okay. Yeah. I have a meeting.
What time?
With a professor at 2. I imagine it won't go beyond 2:30.
Okay. All right. Yeah, I'll definitely be here past 2:30.
Okay. All right.
Yep.
I'll see you.
See you.
Spring break, Professor.
Yeah, you too.
Okay. Could you explain to me why we
there is this always number in direction of hitting first substituent. And so if we number 1, 2, we hit a chlorine at 1. If we number the other way, we hit a chlorine at 2. So we want to keep our 1 on that chlorine.
Okay, and then, so here, like, our double bond is in between 1 and 2, so is that rule only for cyclo?
Yeah.
Okay.
So these two rules only apply to cycle, but
Oh, okay.
so that's cycle.
Gotcha.
Yeah.
But, like, you can do it here, because we put the double bond in the middle somewhere. It can't be, like, 1, 2.
Yeah, if you just want to, in that case, you just number it, so like just give the double bond the lowest one.
Okay. And then, last thing.
Yep.
Could you explain, like, you were saying you can't use cis trans here? Because there's more
Yeah.
than, is it because there's more than 2 different substituents?
If you have more than 2 substituents on a double bond, you can't use cis trans. Because
You can prioritize.
cis trans is basically for, very simple double bonds where there's hydrogen on both carbons
Okay.
around. But anytime we move past that, cis trans isn't
Okay.
acceptable.
So it's like if there's more than 2 different things, or just more than 2 things?
I think it's fine even if they're. I think it's fine if they're different things.
Okay.
So you could have on one side of methyl and on the other side of bromo, and I think you could use cis trans then.
Okay.
But basically,
You're
if you've got, if you've got two hydrogens,
Then you have to use EC.
or at least if you have to have 2 hydrogens to use cis trans.
Oh.
That's
okay.
basically
Okay.
yeah.
Cool. All right. Thank
Yep.
you. Have a great break.
Thank you, have a
Yeah.
good birthday.
Yep.
Takes-